All right, so for tonight's training, we're going to talk through the basics of pump operation and specifically doing the math on what the pump discharge pressure we're looking for from any given scenario for delivering an effective fire flow to a fire. So this all, just note it's U.S. equation, so U.S. Imperial system, not metric. I understand metric is easier to work with and you can get away with a lot more that way, but we're using PSI on all of our trucks, so we're going to do everything in PSI just for the simplicity of the system and what we need. So one big equation that we need to know. Well, one equation with a lot of smaller components. And that equation is pump discharge pressure, PDP, is equal to the nozzle pressure, NP, plus the friction loss, plus the appliance loss, plus the change in head, or the elevation difference between our pump and the fire itself, or wherever we're trying to discharge water at a given rate to. So what this does, this equation gives us the pressure that you need to have the output of the pump displaying. Obviously, if the nozzle pattern is no good, turn up the pressure. If the guys are being thrown around by what pressure you're delivering, turn it down. There's nothing saying that this is the only one possible way of doing this, but this is a way to do it in kind of a mathematically rigorous and in the more engineering way to handle this versus a simple give me more pressure, give me less pressure. So we'll look at this equation piece by piece, and then we'll run through a couple of examples on how to actually apply this for a few given scenarios. So first part of that equation, nozzle pressure. Nozzle pressure is the pressure we need to deliver to the start of the nozzle for the nozzle to output an effective pattern. We want an effective pattern out of the nozzle because this is what does a good job putting water onto the fire. It creates the pattern we want it to, either a smooth, solid stream or a well-distributed fog that's being distributed effectively across the space. Both of those are really important, and if we're not delivering enough pressure, the stream quality is going to degrade. So when we look at this handful of nozzles that we're realistically considering, first, smooth bore. We have a couple of smooth bore nozzles on our trucks. These obviously require the lowest amount of pressure. They need about 50 psi at the tip, or at the entrance to the nozzle. I mean, the reason for this, smooth bore nozzle is pretty simple, and it just kind of tapers down, and and that's it. Very, very simple, single piece of metal, so water flowing through, doesn't encounter a lot of resistance, it just kind of gets necked down, and then that gives us a good pattern out the end. So smooth bore is the easiest one. We have the kind of secondary smooth bore variant of the master stream, which we do have a master stream. Smooth bore master stream. And that is about 80 psi. So not too much higher. That one's a little easier, especially if you're using the master stream off of the truck. Just watch the pattern. If it's getting where you need it to, then it's working. And you can obviously kind of tell by the gauges too if it's working all right. So then we get into some of the more specific nozzle types, the more interesting ones. Fog nozzle, which is what we have on damn near everything. Fog nozzle, we need about 100 psi at the entrance to that nozzle. This is because you've got a lot more moving parts inside of that nozzle. Here, and take a stab at trying to sketch it out. So you got water coming in, you've got the bail. It's this big like ball valve looking guy. comes in, then it comes out, and then there's like some constricting plates in there that move, and then there's a spinning set of teeth at the end. So what you've got to do is account for all of that mechanism and these pretty tight constrictions. So water flows in, it kind of gets necked down to get through the ball valve. It's got a real tight constriction, and then it's got to make a pattern out the sides of the nozzle. So you're doing a lot more with it. It requires a higher PSI for that to function correctly. So 100 PSI for a fog nozzle. It's an easy one to remember also. On the wildland side of the house, we've got the Forester nozzle. This is that funky old looking guy that's got a weird dial here and bit that comes off for like a partial fog nozzle and partial straight stream. Designed for wildland ops. They're kind of light, they're easy to carry, etc. That guy needs 50 PSI. Whoops, I actually write the number. And then the standard kind of variable pattern, the little Twisto red polycarbonate nozzles, variable. We got to deliver, again, about 100 PSI to those. Obviously, that's a little bit more variable, but again, it's a pretty tight constriction, and to get a very nice clean pattern out of those nozzles, we need to deliver a fair bit of pressure to them. So, similar to fog. Okay, so that handles nozzle pressure. That's the first part of this 4-part equation that we need to kind of know and understand to be effective at delivering water to a fire. Second, friction loss. Friction loss is kind of the broad term that encompasses the resistance intrinsic to the hose of water movement. This can be either because of the hose itself, the jacketing is rough or something to that effect, or it can be because of the water bumping into itself. Both are real causes of friction that slow down the flow of water before it gets to the actual fire itself. So we see kind of two different ways of that happening. I'm going to sketch in. There's our edge of the hose and edge of the hose. So as water flows slowly, we get nice kind of bands of flow like this. It's faster in the middle, slower on the outside. This is laminar flow. I'll finish sketching that. Right. So laminar. Laminar meaning sheets, so water is sliding nicely across itself in sheets of flow, nice and smooth. Think a quick but calm stream. So that's a laminar flow kind of scenario. Laminar flow is good. It's low velocity, but low loss, but very smooth. Now, that doesn't do a great job representing what water movement in a fire hose is actually like. We're tending to flow pretty high velocity. I mean, you see how quickly a line is charged when you pull the valve open, and it's moving pretty fast, and there's a lot going on. So, sketching a more realistic scenario. Water flow is a lot more chaotic. So you get some just disjointed, no pattern at all, doing all kinds of random stuff, bumping into itself, bumping into the wall, all kinds of things that cause the water to slow down. So this is turbulent flow. Turbulent flow is a more realistic representation of what we're seeing in our hoses. This is kind of what you see in a fast-moving creek, lots of movement, but it seems to be pretty inefficient. It's because it is. There's the friction of the water against the edges, friction of the water against itself as it keeps crashing into itself. This is more of what we're seeing. So what we understand now, because of this nature of flow, friction is going to be dictated by a few things. So turbulent flow, high velocity, and it's chaotic. So therefore it's lossy. Okay, so how do we figure out this friction? There's a lot going on. Obviously, these are all realistic representations, but they're not either entirely complete, and there's approximations built into them. So friction itself dictated by lining of the hose. Obviously, a rubber jacketed, nice new wildland hose, or rubber jacketed supply line, or just the supply line that's all plastic, garden hose, nice new garden hose, things like that. Those are going to have lower friction than a canvas hose or a canvas inside of canvas. This makes sense. Canvas has a lot of friction. It's really good at not having holes worn through it as you drag it over pavement, but it doesn't do a great job allowing water to pass by smoothly. So smooth is equal to less friction, and rough equal to more friction. Length is the other critical one. Obviously, friction is it's the force applied over that whole area. So length matters. Longer hose means that you have more friction over the length of that, so you need to drive it with more pressure. Shorter means less friction, so you need to drive it with less pressure. So also dictated by velocity. Specifically, it's dictated by the square of the velocity. So as the velocity increases, the amount of friction increases, but in a nonlinear way. So if our velocity is, so we're flowing at like, 2 feet per second, we get some value x. As soon as we increase that flow, we just double that to 4. That's x squared. So as we increase that even more, so we just double that again, we go up to 8. This turns into, so it increases kind of in a nice steep curve. That's not very good. Increases in a steep curve as you increase the speed of the flow. That's because it interacts more with the edges of what's going on. So something to think about. Lower pressure means a lower flow rate. Probably also means a lower amount of friction. So think that way. If we're really driving something hard, it's going to increase the amount of friction in a nonlinear way as we go. Then, most importantly, it's related to the diameter of the hose. So, for those that don't remember, you got generic hose. There's a jacket and then a lining on the inside. What we're measuring is that inner diameter. So that's what matters the most. That dictates how much surface area is in contact with the water, and therefore how much friction we're actually going to see. So as we look at that a little bit more closely, So an 1.75" hose, so 1.75" internal diameter, has about roughly half the friction as an 1.5". So for a relatively small increase in the diameter of the hose, which means we're delivering more water, we decrease the friction by 50%, which is substantial, and it's a big deal, which is why we try and use bigger hose to do supply operations. Obviously, you could run a garden hose the whole distance. It would just take forever. So if you can use 5-inch, that's the way to go. So it's also the pressure component. Once all other things held equal, pressure doesn't matter. It's just the flow of water through the hose that dictates the friction loss in it, not the pressure at which the water is flowing, if that makes any sense at all. So let's look at some nominal friction losses. Nominal. And we're calling these factors because they are specific. We're going to clean that up. Because they're specific to 100-foot lengths of hose. So this is loss per 100 feet. So for a 1-inch wildland hose, and this is out of the IRPG, that gives us 10 psi at a flow rate of 20 GPM. A 1.5-inch wildland hose, which means it's not jacketed on the inside to the same extent as a structure hose, so it's a little rougher. That gives us 3 psi. Note that we're at 30 GPM though. So like wildland mode, slow, easy delivery of water, not aggressive delivery of water. As we increase that flow rate, so we go up to 60 GPM, that turns into 13 psi. And again, these are all per 100 feet. So we go up to 13 psi as we increase that flow rate to 60 GPM. So moving into structure hose options, so a 1.75", that is about 30 psi, and that is at 150 GPM. 2-inch is going to be about 20 psi, but we're increasing the flow rate, so 175 GPM. 2.5, 15 psi. Note that it's not linear. It's related to the diameter and the flow rate at the same time, so you can't quite do it as a simple, easy, just make an approximation. So this is going to be at 250 GPM. Okay, so these are handy kind of things to have on the pump chart. Easy enough. We can kind of use these as good rules of thumb factors. If you want to be super cool about it, or you're using something that you have an odd diameter or odd characteristics and you can't find it in the pump chart, you get to do the math the hard way. And by the hard way, it's really not that bad. It's just one kind of small equation that'll handle it just fine. So if we're doing this in the strict sense, or rigorous, we do that math as friction loss is equal to C, some nominal coefficient, multiplied by Q over 100 squared times length over 100. Okay, so Q, flow rate, GPM, C, coefficient, it's from table, and L is length in feet. Okay, so what is this C factor? It basically accounts for that diameter. So for a handful of different diameters, I'm using the diameter symbol because it's faster to write. Break that out as 1 inch. That C factor is 150. At 1.5 inches, 24. 1.75, so 1.75 inches, 15.5, 2.5, that's 2, and then at 5, so 5-inch diameter, we're at 0.08 on the C. So noticing as the diameter increases, that cohesion friction factor coefficient decreases pretty substantially as the hose size gets bigger. So if you have the option and you have time and you have the water, go with a bigger diameter. It's going to be more efficient and more effective to deliver water to your fire. Okay, so there is our friction loss. Relatively straightforward, nothing to be scared of. Next is appliance loss. Appliance loss is more simple, and we're using bigger, broader strokes to approximate this. As you introduce a piece of system to your water delivery apparatus, so you add in a gated Y, you add in a standpipe connection, you add in piping through another truck, things like that, you add more friction to the system. Same as if you add any sharp bends, any elbows, any things like that cause the water to kind of hit a hard stop and kind of shockwave back and slow down. So appliance losses, really the important ones to know about. So gated Y, that's about 5 psi. So this is for your just standard, water comes in this way, and then it splits in half. And sometimes you can have a valve. So there's 2 valves on the side, and you can open it up, close it. That's about a 5 psi loss because it's hitting a solid surface, or a relatively solid surface. Obviously, if you're making these, you're doing as good of a job as you can to smooth that edge and to smooth that corner right there. So alright, so gated Y, about 5 psi loss at the appliance itself. So other one to be really thinking about is the deck gun. So on engine 83, there's some 90-degree bends and some stuff going on in the pipes. We got to account for it somehow. That's about 10 psi. So nothing to stress about. That's easy, and you'll see it has so low nozzle pressure. Pump running at idle does a pretty good job handling it. So appliance loss, not super common, but something to know about. That 5 psi could be like, why am I not getting a good pattern? It's enough to throw you off a bit. Okay, so last factor that's still important, delta H, head loss or gain. This is all a factor of elevation. So what does this mean? Or how do we get here? Let's take a nominal quantity of water. Let's say we have a container that is, use the fatter pen. I have a container that is 1 inch by 1 inch, and it's a square. And then I take that down, and that's 1 foot long on that long axis, and I stand it up. So 1 inch, and then this is another inch. Okay, so 1 square inch of area, and then this is over 1 foot, and that is entirely full of water. Okay, so how much weight how much does that water weigh? that weight, so that unit of water is going to weigh 0.434 pounds for that nominal value. Pounds weight, pound force, same thing at this given circumstances because we're on Earth and we're not moving it. So what does this mean? For 1 foot of pressure head, so at 1 foot deep, or if you have to move water, hold water at 1 foot up, that's 0.434 pounds per square inch. So that's why we did 1 inch. So therefore, 1 foot elevation is going to be equal to 0.434 psi of either head loss or head gain. So we'll just call it that and not say it's plus or minus. We'll have to make that decision based on what the elevation of a given delivery point is. So let's look at a scenario. I've got a fire truck here. I'll use that. Got a fire truck over here. It's sitting on the ground. Then it's up on some embankment. There's some space, and then okay. So there's 2 fires. Fire 1 is down here. And then it threw a spot, and then there's fire 2 up here. And same engine's going to be delivering water to these, so we'll do some math to see what the elevation difference and how we account for that ends up being. So from our nominal baseline elevation, so that's at the pump panel, it's 5 feet down to where that fire is located. And then to this other fire, it's another 5 feet up. And then to make that attack, obviously we're going to stretch a line from here, go down, put that fire out, and we're going to stretch a line, use the same line, and just keep going and go put that fire out. So discounting the lengths, we're not even going to talk about that for this moment. What's the elevation component of our pump pressure and what we need to think about? So for this first fire, so A and B, fire A, that's 5 feet down. So 5 feet times 0.434 psi per foot, that gives us 2.17 psi. Is that psi I have to pump against, or is that psi I don't have to pump? Because we're going down, it's psi I don't have to pump. So the just neutral amount of pressure that we'll see at the nozzle is going to be 2.17 psi if I don't run the pump at all. Obviously, that's not enough to actually do an effective job giving you a pattern at a nozzle, but it is enough that you can flow water anyway. And if it's a really long way, it'll do a lot. So 2.17 psi positive, or arguably, actually it's negative in these contexts because we're going down. We don't have to account for it in what we're delivering at the pump panel. For fire B, that is going to be plus 5 feet. I'll say minus the 5 there. So same math, equal to 2.17 psi positive. So I have to deliver 2.17 additional psi at the pump panel to account for that elevation difference right there. Okay, why is it only 5 feet for fire B? Why isn't it 10? Hose is going down 5 and then coming up a total of 10. Well, it all balances out. So you would end up doing the math as 5 feet down, then 5 feet up, then 5 feet up. That's still equal to 5 feet. So it's all relative to that baseline elevation. It's not a question of total elevation, which that'd be another 5 feet, not 10 feet. So don't use 10 feet. It's only the difference relative to your pump. So fire engine right there. Difference relative to that elevation there. Okay, so keep those contexts in mind. We'll walk through a couple of scenarios as we go through this. All right, so just to summarize, and so it's fresh in everyone's mind, pump discharge pressure is equal. Here, pump discharge pressure, PDP, is equal to the nozzle pressure plus the friction loss plus the appliance loss plus the change in height. That change in height obviously multiplied by 0.434 psi per foot. So keep that equation in mind. We'll go through a couple of examples. So for this first example, I've got a fire engine and I show up on a little trash fire. So some kind of just crappy looking trash fire over here. Okay, cool, no big deal. I can handle this with a hand line. So stretching that hand line out. We'll change that just a little bit so it's a little more helpful. There. So nozzle, truck, obviously, 81. So this distance is 250 feet. That's 1 3/4 inch hand line. So 250 feet long, we know that. Fog nozzle on the tip. And it's level ground. So something in a parking lot or whatever. Okay, so this is straightforward, relative. It has the fewest moving parts, and it's like one easy step. Not really, but we can get through it. So nozzle pressure. That's going to be equal to fog, which is 100 psi. Our friction loss, we'll do it with the easy way first. So 250 feet times 30 psi per 100 feet. That's going to be equal to 75 psi. So that's a nominal friction loss. Are there any appliances? No. Straight line out to the fire. Easy. So AL equals 0. We don't have to worry about that. Let's do the friction loss the harder way though, just for fun. So friction loss, we'll do that as equal to C times Q over 100 squared times L over 100. C from the table is 15.5. We're going to assume a flow of 150 GPM because that's what's assumed in that 30 value. So they'll be close-ish. And then we can work through this. So FL equals 15.5 times 150 over 100 squared times the length of, what was that, 250 feet over 100. So friction loss then with the stricter method is going to be equal to 87.18 psi. Okay, so it's relatively close. 87, 75. If you're having trouble with the nozzle, turn it up. If you're not, it's fine. So 75 is a good working number, but 87, pretty close. These formulas are relatively comparable. Elevation change, none. So we don't have to worry about that at all. So what does our total end up looking like? PDP equal 100, that's our nozzle pressure, plus 75, just because it's easier, and then plus 0, because there's no head and no appliance loss. So 175 is what we need to charge this from the pump panel. Nice and easy. This is a pretty long line, so it's going to be more. A shorter line is going to be obviously a lower PSI on that initial delivery. So there you go. First example, 175 PSI out the door. Let's look at a second example. So this is going to be a little bit more fun. We've got a fire truck. Wow, that's weird. So you got a fire truck, and then we've got kind of a big-ish fire, or we got a fire that covers a lot of area. Wildland fire, whatever. So we're going to attack both flanks of this because the head's over here and it's looking mean. So we're going to go after the flanks and kind of the back of it and work our way up and pinch around. So what does this mean for our delivery? We're going to do a long horizontal standpipe out to a gated Y. Then from there, we're going to take a line out and then another line out and hit those flanks. Okay, so let's see what we have. This is 200 feet, 2.5 hose, gated Y, and then this is 100 feet of 1.75" with a fog nozzle, because we're just using easy stuff. And then this is 100 feet of 1.5", again with a fog nozzle. So, how much pressure do we need to deliver to this system? Think it through a little bit of how we're going to try and account for both of these at the same time. Do I need to charge? Oh yeah, I forgot to mention, this is also 75 feet up. So this is plus 75 feet relative to the pump panel. So 75 foot of elevation change, no big deal. So what we're going to do, we're going to look at the most resistive leg of the system and drive based on that, because everything else will work if we handle the most resistive side first. So we'll do this in two pieces. Do this first line, then the second line. We can check this one and see, but since it's 1.75 inches, it's going to have less friction than this 1.5 inches. So the 1.5 inches is going to be the most resistive, and we know that. If we scroll back up, we can look at our nominal factors. It's pretty significantly different. So let's do the math. Make sure I have the right sheet open. So, nozzle pressure, 100 psi, since these are fog nozzles. Friction loss, first piece, so the 2.5. We'll just use the easy one and say it's 15 psi per 100 foot. And it's 200 feet long. And then we're going to look at the 1.5 inches. This is further down. We don't have an easy factor for the 1.5 inches because remember, no one likes to use 1.5 anymore. So we're going to use the equation. So C equal, or whoops, that's not right. That friction loss is equal to C Q over 100 squared times L over 100. C is equal for 1.5 inches. We'll use 24. We'll assume a Q of 150. We're using a Q of 250 GPM up here. Okay, so how does this work out? FL equal 24 times 150 over 100 squared times, this is 100 foot length, so that's 1. So friction loss equal to 54 psi. if we wanted to do this for the 1 3/4, just for fun, because we have plenty of time and this is no big deal. Friction loss then would be equal to its C is going to be, assuming the same GPM, its C is going to be 15.5. So 15.5 times 150 over 100 squared, that's only going to be 34.88 psi. So we look at that, total is this 15 over 100 times 200. Hold on while I do the math. I forgot to work that out in advance. All right, so that is 30 psi. Okay, so we'll look at the total there. We have an appliance loss as well in this one. So appliance loss is equal to 5 psi because of that Y. And a head loss, so because we're going uphill, 75 feet. So 75 times 0.434, that's going to be equal to 32.55 psi. So what does our total pump discharge pressure end up being? PDP equals 100 nozzle pressure plus, we will sum up these friction losses. So 30 plus 54, because they're not parallel, we're running both of them in sequence, so we have to capture both of them, plus 5 psi for that Y, plus 32.55 psi for that elevation. So PDP equals, hold on, let me make sure I have this math right because I screwed it up earlier. (221.55 psi). So that's a fair bit of pressure. That's a lot of pressure, but you got to think about this system. This is 300 feet of hose going up 75 feet, and there's a lot going on. So that's actually pretty reasonable. This would obviously be delivered by a larger engine. Brush truck isn't capable of doing this. But off of especially a Type 1, this is no challenge, and this is a very workable kind of scenario. So about 225 psi, start to get up into that range. If everything's working okay, then it's great. You can dial it down if you want to, but this is a good starting pressure where you can work. So 225 pounds at the panel, and there you go. Okay, so let's look at a third example. Okay, so this one, we've got, I'm going to use different colors now. I've got a fire engine here. I got a big Type 1 engine right there. Then I've got a Type 3 engine out here. And then I've got something burning over here. And then obviously, this is all on a grade. So fire's up here. My Type 1 is down here. My Type 3 is over here. And then we're going to be delivering a lot of flow over to that fire. So let's look at our hose lay. So we're going to run a supply line over to there. It's a supply line, so we're going to go as big of a diameter as we can. That's going to be 500 feet of 5-inch. That's going to run about 300 GPM. So a lot of water, but that's okay. Next, we've got another 250 feet or so to deliver water to the fire itself. So 250 of 1 3/4 attack line, and that's only flowing at 150 GPM. So let's look at our elevation differences between these 2 points. Between our first engine and second engine, we've got a 50-foot elevation difference. Then between our second engine and the fire, we're going to have a smaller elevation difference, only 25 feet. Obviously, this is not to scale. Okay, so there's our scenario. What pressure do I need to run each truck at? Let's assume that there's no conservation of pressure between here. So there's a hard stop, and that pressure is not transmitted through. Like we're dumping into a porta pond and then pulling from the porta pond to discharge out. So pressure is not conserved. So let's look at this math. First leg 1. And we'll have leg 2. Leg 1, I forgot to draw that in. Okay, so this is our supply to the end to our attack engine. So supply engine to the attack engine, PDP equal NP plus FL, plus AL plus delta H. Okay, so no nozzle, no appliances. Yeah, at least we're not including any for now. So it's just friction and the elevation difference. So friction loss is going to be equal to, because it's 5-inch and we don't have a handy factor for it, we'll just do the math. C times Q over 100 squared times L over 100. FL equals 0.08 times, this was 300 GPM and 500 feet. Friction loss equals, anyone guessing, 3.6 PSI. Not much at all, which is awesome. So this pump doesn't have to work that hard. So it's actually a good, we can put smaller pumps on this and it's not such a big deal. So 3.6 PSI of friction loss for 500 feet. So big is good, especially for water delivery. Head loss from that elevation change. So delta H is equal to 50 feet times 0.434 PSI per foot. That's going to be equal to 21.7 PSI. So PDP for leg 1 or at engine 833, that's going to be about 25.3 PSI. Okay, is that reasonable? No, that's a little low actually. And it's a little low just from a practical standpoint of, are we able to deliver that low of a pressure successfully? And we really can't. So just have the pump in idle and deliver about 50. So more like 50 PSI. That'll do a better job handling stuff. It's not that hard of work. But, think about taking it a little higher. Go a little higher. No big deal, but it's pretty low. That's nice. The pump doesn't have to work super hard. It's good for gas mileage, things like that. So leg 2, this is going to be the attack engine and what it has to do. So nozzle pressure for the attack engine is 100, because it's a fog nozzle again, as always. Any appliance loss here? No. Let's look at friction loss. It's 250 feet of something at 30 per 100, so 75 PSI there. And then our delta H is equal to 25 times 0.434. That's equal to 10.85. So PDP for leg 2 is going to be equal to 100 plus 75 plus 10.85. That's going to be equal to 185.85 psi. So this engine working harder. And it's working harder mostly because of that appliance at the end of the nozzle. So if you don't have a nozzle on it, you don't have to work as hard. So the legs where there's no nozzle connections, not as big of a deal. But where we have that nozzle, that adds a lot more effort to our attack line effort. And so that pump is going to end up working harder relative to this guy. Slow poke. You're relaxed. That's a good spot to hang out by, nice and chill. This is where all the action's happening. It's nice and easy on the other side. Even though it's 500-foot push, it's still a large diameter and there's no nozzle to work with. Okay, so there's a quick, simple introduction to pump flow, fire calculations. There's the big equation you need. Pump discharge pressure equal to nozzle pressure plus friction loss plus appliance loss plus the change in elevation head. With this one equation, you can do an awful lot to work out how we're effectively delivering water to fires and do a good job not overdriving or underdriving something, and you get to look like a pro when you're delivering water.